Casting out nines is a sanity test to ensure that hand computations of sums, differences, products, and quotients of integers are correct. By looking at the digital roots of the inputs and outputs, the casting out nines method can help one check arithmetic calculations. The method is so simple that most schoolchildren can apply it. Checking arithmetic using remainders, counting and addition. Suppose you are teaching two younger children. Child A collects a pile of sticks and has them on her table. Child B also collects a pile of sticks and has them on his table. Suppose you then have the children group the sticks on their own tables into bundles of 9 sticks, with some remaining. Child A has several bundles of 9 sticks and 2 left over. Child B has several bundles of 9 sticks and 3 left over. Now have the children put all the sticks together on a table at the front of the classroom. Group them in groups of 9. How many sticks will be outside of the bundle of 9 sticks now? It should be still 5. Note that if one child had 5 extra and another child had 6 extra, i.e., 11 total, then the children could group 9 of those together and report 2 remaining. Still, if there is no error, the sum of the sticks left over initially and the group of sticks left over when you are done should agree, allowing for adding or subtracting some multiple of 9 from the total. You know, if the children both claimed 1 extra outside their bundles of 9 each and now they claim 4 extra in the combined pile, something is wrong. What these children have done is the concrete version of casting out 9s. Algebra students. Pile A has plus A, where X is the number of bundles of 9 sticks for student A and R are the ones left outside bundles on student A's table. Pile B has plus B, where Y is the number of bundles of 9 sticks for student B and B are the ones left outside bundles on student B's table. Total 9 plus, given in the example, A equals 2 and B equals 3. The remaining sticks, once you group the total into bundles of 9, should be A plus B, which in this example would be 5. Remember that if greater than 9, then the number remaining that you see may be, where n is some whole number. Example: suppose a student is to add 12 plus 11. Suppose they tell you the answer is 22. They can know this is incorrect if they cast out 9s. 12 equals 9 plus 3, 1 equals 9 plus 2. Your answer should have 3 plus 2 equals 5 outside your bundle of 9s. 22 equals 18 plus 4, which is incorrect. The correct answer is 23, which is 18 plus 5. The desired range for a remainder is between 0 and 8. Otherwise, the children may report several different numbers as answers in some problems. You may untie bundles or group loose sticks into bundles until the number of the remaining sticks is some number between and including 0 through 8. Students will forget to carry A1 here and be off by a few points in an addition there. Usually they will not be off by 9 points. This method may be used to check adding multiple numbers together. Suppose you ask the children to add 8 plus 9 plus 12 plus 4. 8, 0, 3, 4 remainders. When bundled into groups of 9, you have 8 plus 3 plus 4 equals 15, not in bundles. You can bundle 9 of 15, leaving 6 loose. The problem was initially 8 plus 9 plus 12 plus 4 equals 33 equals plus 6, so you now have 3 bundles of 9 and 6 outside bundles. A child tells you the answer is 28 equals plus 1. You know this is incorrect, as some sticks outside of bundles would have to magically disappear. Notice that we were able to discard that entire second pile of 9 from the remainder immediately. In the third pile of 12, we were able to immediately cast out 9 of those sticks. It leads to the common name for this technique of casting out 9s. You may expect 12 and end up showing 3 extra. The missing 9 were bundled. You may expect 23 and end up showing 5 extra. The missing 18 were bundled in 2 groups of 9. The sticks outside the bundles in Group A and those outside bundles Group B should agree with the number outside bundles when all the sticks are piled together, plus or minus some multiple of the number of sticks per bundle. Subtraction. Could this method work for subtraction? Child A has 5 bundles of 9 and 4 loose outside bundles. Child B takes 3 bundles of 9 and 2 loose outside bundles. You end up with 2 bundles of 9 and 2 loose outside bundles. 49 equals plus 4, 29 equals plus 2, blank, 20 equals plus 2. Now you will run into the following type of difficulty. 28 equals plus 1 to 14 equals plus 5, blank, 14 equals minus 4. The problem is in the loose sticks. You cannot have the children carry away 5 sticks from a pile with 1 stick in it. The idea to use is to open a bundle of 9 and add these 9 to the lone loose stick. 28 equals plus 10 to 14 equals plus 5, blank, 14 equals plus 5. Notice mathematically that the answer is still 14, i.e. minus 4 equals 18 to 4 equals 14 versus plus 5 equals 14 if you come up with a negative number of loose items. You missed an earlier opportunity to borrow. This may be corrected later by opening any number of bundles and adding that many groups of 9 to the total of loose sticks. This should yielding 0 to 8 loose items. Notice that to reverse the subtraction you add 14 equals plus 5 plus 14 equals plus 5, blank, 28 equals plus 10 equals plus 1. So notice that this process has needed to use the idea of borrowing in the subtraction problem and carrying when the total number of loose sticks are more than 9. Suppose you expect 4 items outside bundles after a subtraction and the child's answer is equivalent to some multiple of 9 plus 2 loose sticks outside of a bundle. You know there is an error. Multiplication. A child has 1 bundle of 9 and 2 loose sticks. You ask them to put 3 times that many on the front table. 3 * 11 equals, perhaps your students don't know their tables to 11 yet. 3 * plus 2 equals, if they restate the problem in terms of 1 bundle of 9 and 2 sticks, they know 3 times as many will be 3 * 9 plus 6 equals 3 bundles, i.e. 3 * 9 is 27 and 3 * 2 loose sticks, which is 6 loose sticks. 27 plus 6 equals 33. 4 * 23 equals 4 * plus 5 equals 23 is 2 bundles of 9 sticks plus 5 more. 8 * 9 plus 20 equals 18 of the 20 loose sticks may be gathered into 2 new bundles, with 2 loose sticks remaining. 10 * 9 plus 2 equals 92. Suppose the student gave the wrong answer and stated 4 * 23 equals 82, because they forgot to carry the 1 in 4 * 3 equals 12. If they know the problem will end with 2 loose sticks remaining, they will know the answer of 1 loose stick must be wrong. 12 * 11 equals 1 bundle plus 3 loose sticks, * 1 bundles and 2 loose sticks equals, the correct answer is 132. 132 equals 90 plus 42 equals 90 plus 36 plus 6 equals 9 * plus 6. We expected 3 * 2 equals 6 loose sticks and we had 6 after bundling 14 bundles of 9. It will always be true that when you multiply two numbers you can multiply the loose sticks in both factors and get information about the number of loose sticks in the product. If the number of loose sticks in the answer product is higher than 9, you may create more bundles using these. It will always be true that the number of loose sticks you expect by multiplying the two numbers together, i.e. 3 * 2 in the problem above, will equal the number of loose sticks in the product plus or minus some multiple of 9. For algebra students, I will show why this is always true. Again, let's suppose a equals 9x plus a and b equals 9y plus b. In other words, both numbers are some multiple of 9 plus some remainder. A * b equals 9x * 9y plus 9x * b plus a * 9y plus of * b equals 9 * 9xy plus bx plus I plus a * b. Multiply a times b and the loose sticks in the result will be equivalent to the product of the loose sticks from a and the loose sticks from b. Since we are working with 9 here, the remainder may be off by a multiple of 9. If it's off by any other number, the calculation was done improperly. Suppose A equals 9x plus 7. Suppose B equals 9y plus 8. A has some bundles and 7 loose sticks. B has some bundles but 9 loose sticks. For asterisk B equals 9 asterisk Z plus 56, where Z is some number. From the algebra above we know that we will end up with 9 times some number Z plus A asterisk B equals 7 asterisk 8. 56 equals 54 plus 2 equals 9 plus 2. If you're multiplying A with a remainder of 7 times B with a remainder of 8, you should obtain a number that is 9n plus 2, where n is some number. Any other remainder, once all possible 9s are subtracted, then 2 would be incorrect. Division: if A, B equals C, then the product C asterisk B equals A should check. Example: if 60/15 equals 4, then 4 asterisk 15 equals 60. Use casting out nines to check the multiplication. Why use 9s? If any number could be used to check arithmetic using bundles of a given size and remainders, then why does everyone pick 9? What is special about it? Let n equals A asterisk 1 plus B asterisk 10 plus C asterisk 100 plus D asterisk 1000. The number could be written as DCBA. Any of these variables could be 0. We have A asterisk 1 B asterisk C asterisk D asterisk. Think of any number that is made only of 9s. Adding 1 to this number will always result in a number that is a 1 followed by zeros. Notice that n equals A plus B plus C plus D plus 9. This tells you that if you divide n by 9, the remainder will be equivalent to A plus B plus C plus D. Instead of doing a division problem, you may simply add up the digits. Example: what is the remainder of 1234 ninths? If you do the division, you will find it's 137 with a remainder of 1. 1234 equals 900 plus 334 equals 900 plus 270 plus 64 equals 900 plus 270 plus 63 plus 1. Alternatively, you could add up the digits from right to left. The first 3 digits equals 9. The remaining digit is 1, which is the remainder when 1234 is divided by 9. You may add up the digits starting at either end when casting out 9s. Sometimes, though, it's convenient when you see numbers which sum to 9 to start there. Immediately in your mind, bundle those 9. This leaves the 1 only among the loose sticks. You may also think of 9 plus 1 equals 10, whose digits sum to 1. A 9 has no effect on the total when counting up the remainder. Note in the number we picked for n, i.e., n equals A asterisk 1 plus B asterisk 10 plus C asterisk 100 plus D asterisk 1000, we could have continued on and added more digits and the same logic would hold. Elementary example: adding digits in numbers gives the remainder from a division by 9. Finding groups of 9s and putting them aside gives the same results. These methods may be combined. Example: add 2 plus 9 plus 3 plus 4 plus 5 plus 7. Answer 30. One student might realize this is plus 3 simply by rearranging the numbers in the addition problem. They might also notice that 30 is 27 plus 3 equals plus 3. The remainder of 3 seems to be correct, so likely the addition has been done correctly. Another student might say 2 plus 9 equals 11. The sum of the digits of 11 equals 2. 2 plus 3 equals 5. 5 plus 4 equals 9. The ninth of may be divided by 9 with 0 remainder, so the sum so far has a 0 remainder. The final two numbers, chapter 5 and 7, when added yield 12. The digits of 12 sum to be 3. This means the remainder, if the sum were added then the total divided by 9, should be 3. Notice that 9s may be discarded or cast out when found, as they do not contribute to the remainder. Since there are several techniques that could be used to get the remainder after division by 9, i.e. performing the actual division by 9, casting out 9s, and adding the digits of numbers, This makes 9 an excellent choice for this type of procedure, i.e. checking arithmetic using a remainder. Because it's so delightful sometimes to save division work simply by spotting a multiple of 9 that may be cast out. This method using 9s is referred to as casting out 9s. Go back and review the elementary section of casting out 9s. See if your new information, i.e. that you can discard 9s as you find them, and add digits together, allow you to check your work even faster. Modular arithmetic. If two numbers have the same remainder once all 9s have been removed, these two numbers are said to be congruent modulo 9. This is written xy. X equals 9z plus y, where z is a positive or negative whole number or 0. In words, this means that x and y differ by a multiple of 9. Congruence means that you can place one object over another and its properties agree. Triangles that you cut out with construction paper and where one fits exactly over the other are said to be congruent. They may be cut out of different colors or may be covered in different designs. This means that all properties don't have to match exactly. In modular arithmetic, in this case in modulo 9, the essential bit is that the remainder after bundling up all the sticks into bundles of 9 is the same number. X equals means how many loose sticks are there remaining after X sticks are gathered into bundles of 9. X is asking what other numbers have the same remainder or number of loose sticks left over after bundling the sticks into bunches of 9. 60 equals 6. This yields one unique answer, i.e. 6. 60 15 because both have 6 remaining after bundles of 9 are removed. Now check 12 plus 14 equals 26. 12 equals 3. Say 12 modulo 9 equals 3. Add the digits of 12 to get 3. 14 equals 5. Say 14 modulo 9 equals 5. Add the digits of 14 to get 5. 26 equals 8. Add the digits of 26 to get 8. This is what we expect. Check 72 asterisk 14 equals 1008. 72 equals 0. The sum of digits is 9, and since you are making bundles of 9, make a bundle of these and leave 0 remaining. Note that a remainder of 0 means this number should be exactly divisible by 9, and it is. 8 by 9 equals 72. Caution here. Set numbers in equals numbers. 14 equals 5. Add the digits to get 5. Remember, you can always check your math on the sum of digits method by dividing by 9 and looking at the remainder. 1008 equals 0. The sum of digits equals 9. Bundle this and leave 0 remaining. Function is another math word you should know. A function is like a computer that you give instructions. Then you put a number into the computer and it will give you the only possible answer. See Wikipedia Modular Arithmetic for a more extended discussion. Further examples. The method involves converting each number into its casting out 9's equivalent, and then redoing the arithmetic. The casting out 9's answer should equal the casting out 9's version of the original answer. Below are examples for using casting out 9's to check addition, subtraction, multiplication, and division. Addition: in each addend, cross out all 9s and pairs of digits that total 9, then add together what remains. These new values are called excesses. Add up leftover digits for each addend until one digit is reached. Now process the sum and also the excesses to get a final excess. Subtraction: multiplication asterisk 8 times 8 is 64, 6 and 4 are 10, 1 and 0 are 1. Division: how it works. The method works because the original numbers are decimal. The modulus is chosen to differ by 1, and casting out is equivalent to taking a digit sum. In general, any two large integers, x and y, expressed in any smaller modulus as x and y, will always have the same sum, difference or product as their originals. This property is also preserved for the digit sum, where the base and the modulus differ by 1. If a calculation was correct before casting out on both sides will preserve correctness. However, it is possible that two previously unequal integers will be identical modulo 9. One should note that the operation does not work on fractions, since a given fractional number does not have a unique representation. A variation on the explanation. A nice trick for very young children to learn to add 9 is to add 10 to the digit and to count back 1. Since we are adding 1 to the tens digit and subtracting 1 from the units digit, the sum of the digits should remain the same. For example, 9 plus 2 equals 11 with 1 plus 1 equals 2. When adding 9 to itself, we would thus expect the sum of the digits to be 9 as follows. 9 plus 9 equals 18, and 9 plus 9 plus 9 equals 27. Let us look at a simple multiplication. 5 times 7 equals 35. Now consider times 5 equals 16 times 5 equals 80, or 7 times equals 7 times 14 equals 98. Any positive integer can be written as 9 times n plus a, where a is a single digit from 0 to 8, and n is any positive integer. Thus, using the distributive rule, times equals 9 times n plus 9 plus ab. Since the first two factors are multiplied by 9, their sums will end up being 9 or 0, leaving us with ab. In our example, a was 7 and b was 5. We would expect that in any base system, the number before that base would behave just like the 9. Limitation to casting out nines. While extremely useful, casting out nines does not catch all errors made while doing calculations. For example, the casting out nines method would not recognize the error in a calculation of 5 times 7 which produce any of the erroneous results 8, 17, 26, etc. In other words, the method only catches erroneous results whose digital root is one of the 8 digits that is different from that of the correct result.